So, welcome students. So, this is our fifth class on the design of drop spillway. We have already designed the drop spillway, and we have in the last class we have already discussed about how to estimate the horizontal pressures. Here we will be discussing the structural design of drop spillway part 2. This lecture highlights the evaluation of strength and stability of different parts of drop spillway against uplift pressure, contact pressure, piping failure and overturning. What is uplift pressure? The uplift pressure happens because if the foundation material gets saturated, so pore water pressure developed, and this hydrostatic pressure acts upward. So, if this hydrostatic pressure acts upward, then it creates one negative pressure in the stability. Second is contact pressure. The contact pressure is nothing but it is the vertical pressure which is acting at the contact surface between the structure as well as the saturated foundation. So, you can see the contact pressure is given by the notation V, which is acting at the base of this foundation, and depending on the location of this V, that is vertical contact pressure, the overturning of the structure will happen. If it acts at the exactly at the centroid of this base section, then there is more stability, otherwise there will be overturning. Then the piping failure mostly occurs at the base of the foundation, which is contacting between the structure and the saturated foundation material. You can see here the piping failure takes place along the contact surface between the structure and the saturated foundation material. So, all the details will be discussing in this class. The upward hydrostatic pressure on the base is due to the pressure transmitted through the seeping water in the saturated foundation material that reduces the self weight of the structure, and this is mostly caused because of the differential head. You can see this figure. At the upstream side there is depth of water, and at the downstream side there is tail water, and the difference between these two water surface elevations is the differential head, and this differential head gives additional energy head, and that is exerted on the saturated foundation material. So, because of that the pore water pressure, the soil pore water pressure develops. For earth foundations, these uplift pressures are assumed to be existing over the entire base area of the spillway. Uplift pressure can be roughly estimated by using the line of creep theory. The line of creep theory talks about how the water moves at the contact surface between the structure and the foundation material. You can see the line of creep goes like this, as I am marking here on this figure. So, along this line generally the water seeps and the piping failure generally occurs. So, by using this line of creep theory along this contact surface, we estimate the uplift pressure. These uplift pressures are generally computed based on what are the water surface elevations at different contact surfaces along this line, the creep line. For stability, the sum of the weight of the structure and all the vertically downward forces acting on it must be greater than the uplift pressure. if the uplift pressure is more, naturally the structure will float. So, generally the uplift pressure is a negative pressure which has to be deducted from the vertical pressure during all these force calculations. Now, coming to contact pressure. The contact pressure occurs due to the vertical and horizontal loadings at the contact surface of the structure and foundation material. You can see this figure. This is a very important figure to understand. This figure shows the plan of base area. You can see this figure. This is the head wall and this is my apron section, and the whole figure on the top shows the plan of the base area. And here I am choosing the axis, the O axis, just at the bottom corner of this upstream part of this. So, this is my upstream edge and my axis is OO. It is assumed that the whole structure is almost rectangular. It has a width of d and length of b. So, the centroid passes through d by 2 and b by 2. So, this is my centroid which is just exactly at the center of this rectangle, and my vertical forces are acting at this location, which is at distance e from the centroid. So, this is my e distance, and z is the distance between this upstream edge and the point at the line, parallel line joining the point where V is acting. So, at this section V is acting, that is the contact force, that is the summation of all these vertical forces minus the uplift pressure force. So, E is called as eccentricity here. If V is acting exactly at the centroid of this base, then naturally the structure will be more stable, but if it is acting at a distance of E from the centroid, which is called as eccentricity, naturally there will be momentum will be occurring. So, that is called as like your bending moment, you have studied, you might have studied. So, that is just like your bending moment, and generally that will cause overturning of the structure. So, this E can be either this positive side to the centroid axis, or it will be towards negative side, that means this side of this centroid. So, before going to calculate the contact pressures, you have to understand this figure, and this contact pressure should be computed for 3 loading conditions before any backfill has been around the spillway, after all the backfill has been placed with no flow over spillway, and the spillway operating at design discharge capacity. So, these are the 3 engineering conditions generally we consider for calculating the contact pressures. For calculating the contact pressure for a rectangular base, we can use the equation P 1 equal to V by A into 1 plus minus 6 E divided by D. Here E is the eccentricity, D is the width of this base, and V is the sum of all the vertical loads acting on the structure, which are equal to weights of all the concrete, earth above footings, water above any part of the structure, and these are acting downward minus the uplift pressure. So, here the uplift pressure is acting upward. So, it will be minus. Then you can calculate what is the resultant vertical load on this, and if it is acting at this centered location, then it is more stable. If it is acting at a distance E from the centroid, that is eccentricity, naturally there will be turning or momentum will be there. Here A is equal to the base area, that is equal to computed as B into D. If E is equal to 0 in this equation, naturally P 1 will be equal to V by A, that is equal to force divided by area, that is equal to your pressure. Now, you have to compute the moment of vertical loads m v. For this, you have to select the OO axis as seen in this figure. From this OO axis, along the upstream edge of the base area at the elevation of the bottom of the apron, you have to select this OO. Let B I be the magnitude of the ith part of the vertical load or weight, because there are different vertical loads. These vertical loads can be because of the head wall, it can be because of the apron, it can be because of the backfill materials. So, these are different vertical load components. So, these are called as V I, and they are acting at a location perpendicular distance between the line of action of the load V I and the axis O, that is equal to L I. Then the moment m v of all such parts of the total vertical force about the O axis can be given by this equation. You know that momentum equal to, or moment equal to force into the length. So, m v equal to sigma V I L I, that equal to V 1 L 1 plus V 2 L 2 plus V n L n, where V I are the different part loads, different part vertical loads, and total resultant vertical load will be equal to summation of all these vertical forces acting on the base of the structure. Then there could be the horizontal loads. The horizontal loads could be because of there is static water table at the upstream side, and let these vertical loads be defined as different parts. Let H I equal to magnitude of the ith part of the horizontal load, Y I is the vertical distance from the line of action of the load H I through its center to the O axis. Then the moment m h of all such parts of the total horizontal force H can be estimated similar as we have done for the vertical loads. So, here m h will be equal to sigma H I O I A, and H will be equal to summation of H I, that is the total horizontal loads. Then the total moment due to vertical loads and horizontal loads can be estimated by this equation, which is m v plus m h, that equal to total moment divided by B will be give you the value of Z, because B is the resultant load, resultant vertical load. So, the total moment will be counted by V times Z. So, Z is the distance from this O axis to the point, to the line passing through this point where this V is acting. So, you can estimate what is the distance Z. By computing this Z, you can check for the stability against tension. So, for stability against tension at the base of head wall, we can estimate what is the eccentricity. From this figure, you can see that d by 2 equal to E plus Z. So, E will be equal to d by 2 minus Z, and for stability against tension, you have to design in such a way that E should be less than d by 6. If you solve this equation, then you will get Z equal to d by 3, or sorry, Z is greater than d by 3. So, that means for stability against tension, Z should be greater than d by 3. The structure is safe against overturning if positive contact pressure exists over the entire base area. So, depending on this position of eccentricity, you can estimate whether the structure will overturn or not. So, to avoid the overturning, you have to design such way that Z is greater than d by 2. Now, next is stability against the piping failure. You can see from this figure that piping defined as the removal of material from the foundation through seepage water as it emerges from the soil below the dam, and this mostly occur when the water table is high. If the upstream water table is high, it creates additional water pressure, and because of this generally the pervious foundation is gets saturated, and when it gets saturated the upstream pressure, the water pressure which is causing the flow of or which is causing generally the saturation of this foundation. So, it will create additional pressure, so that this water will move along with the soil particles and it will make a pipe like structure, and if there is more loss of the soil materials along this pipeline, then the structure will fail. The velocity of seepage depends on the length of flow path. Failures due to piping may result from subsurface erosion or heave. So, because of this the subsurface erosion causes, that means the soil particles along this line they emerges out at the downstream section, and sometimes this creates quicksand condition. You might have studied already that what is quicksand condition. The seepage could occur through earth foundations as flow through the foundation material itself. It can directly flow through this foundation material as shown in this figure, or along the line of least resistance, which is the line of contact between the spillway and foundation. That means, this seepage may occur also along this contact surface as I am showing in this diagram. That means, it will pass through this line, and this is called as the line of creep, as we have studied in the previous slides. Now, for the stability against piping failure, the design against piping failure is based on the line of creep theory, and it is postulated by W. G. Bly and further revised by E. W. Lane. So, Lane's theory is the most advanced one. So, that is why we will use the Lane's theory for all our designs. The line of creep is the line of contact between the dam and cutoff or toe walls with the foundation that produces less resistance to percolation than any other path through the foundation material. If you will see this figure, the values, that is LV1, LV2, LV3 and LV4, these are all steep contacts, the vertical contacts, and the distance LH1, LH2 and LH3 in this figure all are horizontal distances, and all these are called as horizontal flat distances if the slope is less than 45 degree. So, we generally calculate the weighted creep length, the effective seepage length. So, the effective or weighted creep length is estimated as 1/3 of all these horizontal distances plus the sum of the vertical distances. So, it is the sum of all the steep contacts and 1/3 of all the contacts flatter than 45 degree between the head water and tail water along the contact surface of the drop spillway and foundation. And capital H is the static water table at the upstream side, which is mostly causing the seepage below the foundation. So, that is why H is the driving head or driving energy head. So, the length theory for safe weighted creep ratio is given by C W. So, C W equal to weighted creep distance, that we have already estimated as summation of L V. So, L V equal to L V 1 plus L V 2 plus L V 3 plus L V 4 and 1/3 of the horizontal distance. So, that equal to 1/3 of L H 1 plus L H 2 plus L H 3 as shown in this figure, divided by capital H. Capital H is the driving or static water head which is causing this seepage or the piping failure. So, for stability against piping, generally the calculated CW value should be greater than the tabular value, and the CW of table value is estimated or it is already computed depending on the different soil type of the foundation material. Otherwise, the depths of cutoff or toe walls have to be increased. If it is less than the table value, then you have to increase the depth, that is LB1 or LB2 or LB3 and LB4, so that the stability against piping failure is achieved. So, these are the different weighted creep ratios of different foundation materials. You can see the for very fine sand and silt, which is having more porosity, it has a greater CW value. So, greater CW value means it is less stable. For fine sand it is 7, medium sand 6, coarse sand 5, fine sand it is 4, medium gravel 3.5, coarse gravel including cobbles that is 3, boulders with some cobbles and gravel 2.5, soft clay 3, medium clay 2, then hard clay 1.8, and the least is very hard clay or hard pan, that is 1.6, that means it is more stable. Clean gravel has 5, clean sand or sand and gravel mixture 6.5, well graded mixtures of sand, silt and less than 15% clay, that is your 5.5, it is more than 15% clay, then it is 4, and for firm clay it is 2.3. So, these are the tabular values of CW. So, our value should be greater than this tabular value. Then, as we have already studied in our previous lecture, so depending on the backfill condition and drainage condition, you can design or you can estimate the elevation of the saturation line Y2. You can see from this figure the case C. Suppose for example, for case C, this Y2 value you can estimate, and that is depending on different water table conditions. If your water table condition is suppose high and the relative permeability between the foundation to backfill material is equal suppose, and drainage condition is A, then for no flow condition I can get Y2 equal to S plus 0.5 F, and this S plus 0.5 F is nothing but the value of Y2, and this Y2 value you can estimate because it is mostly responsible for estimating how much is my water table depth. So, the saturation line shows the water table depth in the backfill material. So, that is why during the load computation, so this Y2 value is very much important. So, this table will be always referred for all these design calculations of this drop spillway. So, everything will be clear with if you will follow a problem, if you will solve a problem. You can see in this problem a drop spillway has to be constructed for a design discharge Q equal to 5.83 cubic, length of wear is 4 meter, total drop is 2.44 meter. If the depth of the toe wall T2 as shown in this figure equal to 0.91 meter, find the required depth of cutoff wall T1 to ensure safety against piping for the following conditions. So, there are 3 conditions given. One is pond above structure with no upstream bomb against head wall, second is pond above structure with upstream bomb and type A drainage, and pond above structure with upstream bomb and type B drainage. And the conditions of foundation material are given. So, it is well graded mixture of sand, silt, clay having clay content 20% which is greater than 15%. Relative permeability of the foundation and fill material is equal and water table is high. So, for the foundation material, that is well graded mixture of sand, silt and clay which having clay content greater than 20%, you can estimate what is your CW value from this table given table, but for designing this you have to estimate what is the value of H as shown in this figure. To estimate the value of H, naturally you have to estimate what is the value of S. S is nothing but it is the depth of end seal. So, as we have studied in the previous classes, S can be estimated by using Q and AL relationship, like by computing the critical depth DC, and DC you know that equal to Q square divided by L square G whole to the power 1 by 3. So, once DC is estimated, so S will be equal to DC divided by 2. So, those calculations can be done in the next slides. So, for estimating S, you have to estimate what is your DC value. So, here by putting the value of Q and L and G equal to 9.81, you can get DC equal to 0.6 meter and S equal to DC by 2, that equal to 0.3 meter. So, here H can be calculated as shown in this figure, that equal to F plus S plus this distance or this height, that equal to T x, and T x is given as 0.25 meter. So, H will be equal to F plus S plus T x, and that equal to 2.44 plus 0.3 plus 0.25 equal to 2.99 meter, because F is already given, that equal to 2.44 meter. So, once H is estimated and we have given T 2 equal to 0.91 meter already. So, I have to estimate what is my T 1 value by using the lens creep theory. I can estimate what is my T 1 value, so that the piping failure will not be happening. Now, for this you have to estimate what is the table value of C w, and for the given condition, well graded mixture of sand, silt and clay and having clay content 20%. So, you can calculate that C w equal to 4. So, for all the estimates you can take C w equal to 4. Now, using lens creep theory, you know that C w h equal to sigma L h, the length of all these horizontal distances, divided by 3 plus the summation of all the vertical distances or the vertical depths. So, in this case, the length of vertical distances will be equal to 2 T 1 plus 2 T 2. If you will see this figure, this is T 1 and this side will be also will be equal to T 1, this is T 2 and this side will be also equal to T 2. So, 2 T 1 plus 2 T 2, and this B is the horizontal distance. So, it will be divided by 3. So, by solving this, you will get 2 T 1 equal to C w h minus B divided by 3 minus 2 T 2, and H I have kept here without putting this value. So, that we can do later on. So, B equal to 4.14 divided by 3 minus 2 into 0.91, because T 2 is given as 0.91. So, we will get 4 H minus 3.2. Now, T 1 will be equal to 2 H minus 1.6. So, whatever the conditions are given, so depending on that the H value will change. So, for this condition, first condition, that is with no upstream bomb, here H is equal to 2.99 meter, and directly you can get T 1 equal to 2 H minus 1.6. So, H is 2.99. So, you will get it is 4.4 meter. So, this is for the first condition. Now, coming to the second condition, that is with upstream bomb and type A drainage. For type A drainage, for the given condition, you can find out what is the value of y 2 as shown in this figure. So, you can estimate what is the value of y 2. So, this is my y 2. So, here I am getting y 2 equal to S plus 0.5 F, that you can estimate from here for no flow condition. So, once this value is known, y 2 equal to S plus 0.5 F, that you can use for your subsequent calculations. So, as shown in this figure, here H equal to y 2 equal to S plus 0.5 F. We have already seen that one, that y 2 equal to S plus 0.5 F. So, you can estimate what is the y 2 value. So, here y 2 equal to 1.52 meter, and this y 2 is corresponding to that is the depth between the saturation line and the line from this bottom of this top of this apron. So, this is my y 2 value. So, that is you can estimate as 1.52 meter, and from the sketch you can get this h equal to y 2 plus T x, because this T x has to be added here. Then you will get this 1.52 that equal to y 2 plus 0.25 that equal to 1.75 meter. So, T 1 will be getting that is 2 h minus 1.6 and h equal to 1.75 meter. So, we will get 1.9 meter. So, my T 1 value is 1.9 meter. Similarly, you can do for the third case. So, for the third case, it is type B drainage. For type B drainage, similarly you can select what is my y 2 value. In this case, you can see the y 2 value is equal to s plus 0.15 f, that you can see from this table. So, this is the distance from this bottom surface to the saturation line. So, once y 2 is known, so by using this you can estimate what is my h value. So, for this first I have to estimate what is my y 2, that equal to s plus 0.15 f, that I can compute here. So, s equal to 0.3 and f equal to 2.44. So, I can get y 2 equal to 0.67 meter, and from the sketch you can get h equal to y 2 plus T x and y 2 equal to here 0.67 plus T x equal to 0.25. So, we are getting 0.92 meter. So, once h is known, this h is known, you can estimate what is T 1, that equal to 2 h minus 1.6. So, by putting the values of h and that is 1.6 here. So, we will get T 1 equal to 0.24 meter. You know that the minimum depth of this cut-off wall should be 1.2 meter, but this value is 0.24 meter, which is much below than that of 1.2 meter. So, for this case you can recommend the minimum value that is equal to 1.2 meter. So, your minimum T 1 value equal to 1.2 meter. So, if you are providing a cut-off wall of depth 1.2 meter, then it is secured from the piping failure. So, this example shows that what are the effect of different earthworm and the drainage condition. It can be drainage condition A, it can be drainage condition B, and it can be no flow, and because of that how the cut-off wall depth is changing, or it can be optimized so that there will not be any piping failure. So, from this lecture we summarized that what are the contact pressures, what is piping failure, what are the main causes of piping failure, and to withstand against the piping failure how we will design our depth of cut-off wall, and what is the optimized depth of cut-off wall, and we discussed about the overturning depending on the uplift pressure and the vertical pressure loads, at what is my z, that is the or the eccentricity, according to that whether it will be overturning or not. Okay. So, this completes our lectures here, and in the next class we will be discussing about how the contact pressures will be estimated by using the line of creep theory. So, we will end our lecture here. Thank you very much.